This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about statics, CE 2301. We're looking at a problem from the sample quiz number 4 involving second moments of area, the moments of inertia, and the products of inertia for composite areas. I've started this and hope to just do it by hand live on the video and not smudge on my drawing and my numbers. So I've started it, but anyway, the shape that we're concerned with is this T shape. The dimensions are all in millimeters, 60, 60, 60. The height is 60 and 60. So first thing I want to know is Y bar. So I'll break it up into two segments. I call segment 1 this horizontal rectangle, and I call segment 2 this little square down here that's 60 by 60. My areas are as shown. I start my chart. My area is 180 by 60, 10,800. My area of segment 2 is just 60 by 60, so it's 3,600. I add those two up, I get 14,400. My Y tilde, the distance from the base to the centroid of each segment, measured from the base, for the rectangle on the top, segment 1, it's the 60 of the square plus half of the height of the rectangle, which is 30. 60 plus 30 is 90. For the square on the bottom, I have 60 divided by 2, half of its height, or 30. My next column is Y tilde A. I just multiply these two columns together. 10,800 times 90 is 972,000. 3,600 times 30 is 108,000. I sum those, I get 1,080,000. Now I'm ready to calculate Y bar, which is just the sum of the Y tilde A's, 1,080,080, divided by the area. Sums is 14,400. I get 75 millimeters. Okay, now I'm going to try to fill these in by hand. The next thing I want to know is Ix prime, the centroidal moment of inertia about the centroidal x-axis. So for that, the first thing I need is the centroidal moment of inertia about the x prime axis of each little piece, the two segments. Call that Ix prime. For this rectangle, the centroid is right there for the rectangle. The moment of inertia about that x-axis, x prime axis, is bh cubed over 12. So that's 180 is the base times 60 cubed over 12. That number works out to be 3.24 10 to the 6th. Remember, I recommend keeping everything in the same exponential of 10 to the 6th, so it makes it easier to add and subtract as you need. I think they all work out to be in that same order of magnitude. For the square that's 60 by 60, the centroidal moment of inertia about the x prime axis is 60. The base times the height, 60 cubed, divided by 12. That equals to 1.08, 10 to the 6th. Now I want to add those up, and I get 4.32, 10 to the 6th. So that's part of my number for this. I'm using the parallel axis theorem for all these problems, and the next component that I need is the AD, in this case y squared term. So what I need now is the dx distance. The distance from the centroid of the overall piece to the centroid of the segment. So for segment 1, the rectangle, the centroid of the overall piece is 75 in the y direction. Centroid of the piece is at 90. It's this column right here, Y tilde. So it's negative 15. For the square on the bottom, I have 75 minus 30, this column right here. So that's equal to 45. Now, I need to do my a dy squared term. That term should be dy. dy squared. I'm just going to square that number, multiply it by the area. Negative 15 squared times 10,800 is 2.43 10 to the 6th. And for the second segment, square 45, multiply it by 3,600, I get 7.29 times 10 to the 6th. I add that column up and I get 9.72 10 to the 6th. Now, Ix prime of the whole composite shape is the sum of the individual Ix primes plus the sum of the a dy squared terms, just the parallel axis theorem. Just add these two columns together, 4.32 plus 9.72 is equal to 14.04 10 to the 6th. My units are, of course, millimeters to the 4th. Put a box around it. Next, I want to know what my radius of gyration about the x-axis is, and that's just, remember, square root of Ix divided by the area. Well, I've got all the numbers I need. That's just the square root of this number, 14.04 10 to the 6th, divided by the area of 14,400. Do the math, take the square root of it. I get that Kx is equal to 31.2 millimeters. Remember, that's the concept of if I took the whole area and put it in a thin ring, but the radius, that's what the radius of that thin ring would be to create the same moment of inertia about the x-axis. It's really the x-prime axis. Okay? The fourth problem is what's the moment of inertia about the centroidal y-prime axis, the vertical axis. And I don't have much room here, but I think I'm going to be alright because of this one fundamental thing. I'm going to first compute my centroidal moments of inertia, Iy prime, which are just bh cubed rotated, or hb cubed if I consider this orientation. So it's just 60 for this rectangle on the top. The base is 60, the height is 180. I cube that. Divide by 12. I get 29.16 10 to the 6th. For the square, it's the same exact number. 60 times 60 cubed, because it's a square, divided by 12. So it's 1.08 10 to the 6th. Add those two numbers up. I get 30.24 10 to the 6th. And now I need my ADX squared term. Oh, this is nice because the centroid of the overall composite shape is at the centroid of the individual pieces. The dx term is 0, so that adx squared term in this case goes to 0. So I'm left with just the sum of my individual centroidal moments of inertia about the y-axis. So I could write that out. It's a sum of the y primes plus the sum of the a dx squared terms. Dx is 0 for both pieces, so it's just the sum of my iy primes. 30.24 10 to the 6th. Finally, I have the product of inertia about the centroidal moment axes, Ix prime, y prime, and once again, this is my lucky day because one of these axes is an axis of symmetry. The product of inertia of that is equal to 0. That's 0 because y prime is axis of symmetry. I wasn't asked it on the sample quiz, but I could ask you what's the polar moment of inertia about its centroidal axis. Remember that is Jo is just equal to Ix prime plus Iy prime, which is equal to 14.04 plus 30.24, which is equal to 44.28 10 to the 6th millimeters to the 4th.